center. So due to this point charge Q, we have some electric field in the radially outward direction. Alright, now due to this electric field, we have some electric flux through this surface, and that electric flux is what we need to find. But this formula works only when the electric field is constant over the surface. Alright, any point on the sphere, we have the same electric field magnitude. Do you understand? So this spherical surface is the Gaussian surface here. So as R tends to infinity, this value decreases to 0. Do you understand? So by symmetry, so the electric flux is same for all the surfaces. So that means we found the electric flux through the entire cylinder using Gauss's law. Flux, now electric field in the vertically upward direction. That means that component of the electric field is 0. In the last class, we were talking about electric flux, right? To calculate the electric flux, we used various formulae, right? Like this one. So the electric flux through a surface of area A is given by the electric field vector dot product with the area vector, or EA cos theta, right? Theta is the angle between the area vector. So what is area vector? So that is a normal vector to the surface. So the angle between the normal vector and the electric field, so that is theta. So then the formula is given by EA cos theta. Or we can simply say that the electric flux is the electric field multiplied by the projection of this area in the perpendicular direction, right? So we used various methods like this to calculate the electric flux. But as a continuation of this, here also we will find the electric flux, but not using these formulae, but using Gauss's law. So what did Gauss say? See, to find the electric flux, so let us consider this simple example. Alright, see here, so we have a spherical surface, okay, it is a spherical shell. Now inside which we have a charge Q. So this is a point charge placed at the center. So due to this point charge Q, we have some electric field in the radially outward direction. Alright, now due to this electric field, we have some electric flux through this surface, and that electric flux is what we need to find. So let us find the electric flux. Alright, so let us find the electric flux. So what is the formula for the electric flux? So that has formula, this electric field multiplied by the area of the surface. Okay, simply we can use this formula, no need of cos theta or anything, simply electric field multiplied by area, because the electric field lines due to the charge Q are in the radially outward direction. So all these electric field lines are perpendicular to the surface of the sphere. So as we know, the radial vector is perpendicular to the surface of the sphere. So that means these electric field lines are perpendicular to the surface. We can simply use the formula electric field multiplied by area, because we have the formula, the electric flux is simply the electric field multiplied by area, if these two are perpendicular. Alright, so this area surface is perpendicular to the electric field. We can simply use the formula electric field multiplied by area. Alright, so let us find the electric field. Now the electric field due to the charge Q, so that has the formula, right? Because all the points on the surface of the sphere are at a constant distance, right? The radius R at a constant distance from the center, from the charge Q. So that means we can write the direct formula for the electric field, KQ divided by R square, because R is constant, KQ divided by R square, or we can say K. So that is 1 divided by 4 pi epsilon 0 KQ divided by R square. So that's all. So this is the electric field due to the charge Q at any point on the surface of the sphere. Okay, done. Now similarly area. So which area? The curved surface area of the sphere. You understand? So what is the formula for the curved surface area of sphere? So that is 4 pi R square. Alright, so that's it. Now if you simplify this, these values get cancelled. So we get simply Q divided by epsilon 0. So that is the value of phi. So that means the electric flux through the surface due to the charge Q. So if you observe, this is independent of R, radius, which means whatever is the radius of the sphere, doesn't matter, the value remains same. Okay, if you take a bigger sphere, so still the electric flux is Q divided by epsilon 0. So that's all. So this is the electric flux. So what is this Q? Q is the total charge inside. So you can write Q is actually Q in. Okay, let us use this symbol to denote this total charge inside. Q in, that means the charge inside that surface. Do you understand? So the total charge inside the surface is Q. Now that Q divided by epsilon 0 will give you the electric flux. So we don't need to use these formulae and all. Simply use the formula Q divided by epsilon 0. This is only for the electric flux through a closed surface, so which contains the charge Q. So the closed surface contains the charge Q. Now we can find the electric flux using this simple formula, which is Q divided by epsilon 0. Now, so this can be generalized also. It need not be a spherical surface. So any surface, you take any surface, closed surface. Now inside that surface we have a charge Q. then the electric flux through this surface can be written as Q divided by epsilon 0. That's all. So it is not necessarily a spherical surface. Alright. So any surface, so that will have the same electric flux. Is that okay?
But we proved the result only for a sphere.
Yeah, we have proved it only for the spherical surface, but this result is true for any surface, any closed surface. We have the same formula. See, suppose it is not a spherical surface, so some different shape, okay? But to find the electric flux, we take the projection of this surface in the perpendicular direction. But what is the surface in the perpendicular direction? That is a sphere. Do you understand? That sphere is perpendicular to the electric field lines. So that means if you take the projection of this surface, okay, the surface of any shape, so that projection will be a sphere only. Do you understand? That means this result is not only true for a spherical surface, even if you take some other surface, the projection of any surface, any closed surface in the perpendicular direction, so that will be a sphere. Do you understand? So that means this formula we can use for any surface, any closed surface, so which has this charge Q. Alright, so inside the closed surface we have the charge Q, then the total electric flux is given by this formula. So Q divided by epsilon 0. Do you understand? So that's it. So that is about Gauss law. Alright, so Gauss law gives you an idea about the electric flux through a closed surface due to a charge Q inside that surface. Alright.
But the charge is at the center. What's the center of this shape?
See, this charge Q need not be at the center of the sphere. It can be anywhere inside the closed surface. But we have done the proof taking the charge Q to be at the center of the sphere. But this result holds even otherwise. You take any charge inside the sphere, okay, the total charge matters, okay, not the position of the charge. So Q is the total charge inside the sphere. Do you understand? So the position of the charge doesn't really matter. This is one of the points about the electric flux, alright. So let us write few points about this Gauss law, alright. So the first point here is simply this formula. See, the electric flux through a closed surface is given by the formula phi equals Q divided by epsilon 0. Alright, that's all. This is a simple formula to find the electric flux through a closed surface which contains the charge Q. Okay, done. What is this charge Q? So sometimes written as Q in. So that is the total charge inside that closed surface. Alright, so Q in is the total charge inside the closed surface. Alright. Now the charge outside are not taken into account. Alright, so we don't consider any charge outside the sphere. Okay, only the charge inside the sphere are considered here. Do you understand? So Q is the total charge inside the sphere. Now next point, this result is true for any surface, any closed surface. Alright, not necessarily for a spherical surface. So this result Q divided by epsilon 0 is the value of electric flux. So this result is true for any closed surface which is called a Gaussian surface. Alright, this closed surface through which we are finding the electric flux. So this is called a Gaussian surface. Alright, so the electric flux through the Gaussian surface is given by the formula this one, Q divided by epsilon 0. That's all. It is called a Gaussian surface. Alright, so the next point is the position of the charge doesn't matter, right? So Q is just the total charge inside. So where is this charge placed inside that closed surface? So that really doesn't matter. Alright, so the position of the charge doesn't matter. Okay, now see, for example, you take this case. So here, what is the electric flux in this case? So let us find the electric flux. So this is the closed surface. Now we have the total charge inside the closed surface. Let us count. Okay, so Q plus Q plus Q plus Q minus Q, which means 3Q is the total charge inside the closed surface. That means what is the electric flux through the surface? That is simply the total charge inside the surface, that is 3Q divided by epsilon 0. Outside we have some charge Q plus Q 2Q. So we don't consider that. So we don't consider the charges outside. Only consider charges inside. So that is 3Q divided by epsilon 0. Do you understand? So that is the total electric flux through the surface. Do you understand? Okay. But this electric field here is due to any charge. Do you understand? Suppose you want to find the electric field at a point on the surface. So that is not only due to the charge inside that sphere or inside the closed surface. That electric field can be due to any charge, okay, inside, outside or anything. So this electric field is not necessarily due to the charge inside the closed surface. Do you understand? So this Q is only the charge inside the closed surface, but this electric field at any point on the surface, so that may be due to any charge. Do you understand? Not necessarily the charge inside. So that is one important point that you have to remember. Do you understand? So these are the points about this Gauss law that you have to remember. So the electric flux through a closed surface is found using this Gauss law. That is simply the total charge inside the closed surface divided by epsilon 0. That will give you the electric flux through the closed surface. Okay. Now mostly we will use this Gauss law to find the electric field due to various objects, right? So various objects of continuous charge distribution. See, we have the formula, the electric flux phi equals, we already know the formula, E multiplied by A. for the simplest case, right? E multiplied by A, area. So that is the electric flux formula. But now we have also written another formula, alright? So Q divided by epsilon. So this is also the formula for the electric flux. So electric flux is given by E multiplied by A. So that is also equal to Q divided by epsilon 0 for a closed surface. Now equating these two expressions, we can get the value of E. Alright, if you want to find the electric field, so use that relation. Okay, E multiplied by A equals Q divided by epsilon 0. Using this relation, we can find the electric field. So to find the electric field also, sometimes we use this Gauss's law. Do you understand? But this formula works only when the electric field is constant over the surface. Alright, what if the electric field is not constant? Then what is the formula for the electric flux? So the electric flux is the integration of E dot dA. Do you understand? So that is the formula for electric flux if this E is not uniform. Okay, so this integration is over the closed surface. Okay, so and that must be equal to Q divided by epsilon 0. Okay, so if the value of E is not constant, you have to use the integration formula. Okay, so if E is constant over the surface, entire surface, the value of E is constant, then we can use that formula, simply E multiplied by A. Is that okay? But generally, for calculations, we always take the Gaussian surface to be a surface on which the electric field value is constant. Otherwise, you have to do this complicated integration. Always you take, for convenience, you take the Gaussian surface to be a surface on which the electric field is constant. Okay, so we have to decide, depending upon the charge, you have to decide on what surface the electric field value is constant. So accordingly, so we have to use the formula. Do you understand? If you take the surface, Gaussian surface, to be a surface with constant electric field or same electric field at every point on the surface, then we can simply use the first formula, E multiplied by A. So that is the electric flux. Do you understand? So that is one formula you have to remember. Okay, so these are all the points about the electric flux using Gauss's law. Okay, so Gauss's law, so we have to remember these points. Okay, so that is about the Gauss's law. So let us use this Gauss's law to find the electric field due to some continuous charge distribution. Okay, so the first one in our list here is electric field due to a point charge, as if we don't know this already. So we have the formula for the electric field due to the point charge q at a distance r. So that has formula kq divided by r square. So we are already familiar with this formula, but we will still do this again because we want to get used to the idea of using Gauss's law to find the electric field. Okay, see, at a point at a distance r from the charge, we have some electric field, say E. Now, is there any other point at which we have the same electric field, at least the magnitude? Apart from this point, is there any other point at which we have the same electric field magnitude? See, the electric field is dependent on the distance, alright, and the charge q. So you take another point at the same distance, alright, same distance r. So that point also has the same electric field, right? At that point also we have the same electric field magnitude E. Do you understand? So you take all the points, connect all the points which have the same electric field magnitude as this point. So we will get a circle. In 2 dimension it is like a circle, in 3D it is a sphere, because any point on a sphere is at a constant distance from the center, which means at any point on the sphere we have the same electric field magnitude. Do you understand? So this spherical surface is the Gaussian surface here. So what is the Gaussian surface? At any point on this surface we have the electric field value same. Do you understand? So we have the Gaussian surface. Now we have to use Gauss law for this Gaussian surface, okay, which is a spherical shape here. So let us find the electric field at any point on the surface, because all these values are same. At any point on the surface the electric field has the same value. So we will find the electric field using Gauss's law. Alright, let us use. So what is the formula for the electric flux? See, this electric flux has two formulae, right? So one is the electric field multiplied by the area. Okay, that is the direct formula for the electric flux. Alright, because the electric field here is perpendicular to the surface here, because the electric field is the radially outward vector which is perpendicular to the spherical surface here. So E multiplied by area. So that is the electric flux. But now by Gauss's law we also have formula for the electric flux. So that equals Q divided by epsilon 0. So the electric flux has two formulae, which is E multiplied by A or Q divided by epsilon. Now equating these two, we will get the electric field, that's all. So electric field is what we need to find. So this gives the electric field. So E multiplied by area. So what is the area of the surface? The curved surface area of a sphere. So that has formula 4 pi r square. Alright, 4 pi r square. So that is the curved surface area of sphere. So E multiplied by A, that equals Q divided by epsilon 0. So that's all. So this will give you our value of E. So that is Q divided by 4 pi, okay, so epsilon 0 R square. So that's all. So that is the formula for electric field. So we can write it in terms of K if you want. 1 divided by 4 pi epsilon 0. So that is K. So K Q divided by R square. So that's all. So that is the formula for the electric field due to a point charge. Okay, so we have the simple formula KQ divided by R square, which you are already familiar with. Okay, but now we have derived this result using Gauss's law. Do you understand? So this is a simple illustration of how we use Gauss's law to find the electric flux or electric field. Do you understand? So what do? We have to find the surface. Which surface? What we call a Gaussian surface, right? You have to find a surface on which the electric field has the same value. In this case, it is a sphere. You understand? A spherical surface. At any point on this sphere, we have the same value for electric field. So that is why we are able to use this formula. This E is a constant. If E has different value, variable value, we can't use this formula. Do you understand? Because E is constant at any point on the surface. So we are able to use this formula and we got the answer E KQ divided by R square. So that is the electric field at any point on the surface. Particularly this point, we want the electric field. So that has the same value. So KQ divided by R square. Do you understand? So that is the formula for electric field due to a point charge. Now this time we've used Gauss's law to find the electric field. Okay. Similarly, we'll take few more examples. So in all the examples, we have to use the same idea. What is the idea? We have to find a Gaussian surface, a surface on which we have the same electric field. On the surface, we should have a constant electric field. Then use this formula, we will be able to get the electric field. Okay. So this is one such example. Now we'll take few more examples. Okay. Here we need to find the electric field due to a spherical shell. See, this need not be a spherical shell. It can be a solid sphere but a conductor. See, as we know, in a charged conductor, the charges are distributed only over the surface. So that is treated more like a spherical shell. Suppose it is a solid sphere but a conductor. So still the charges are only on the surface of the sphere. So that is treated more like a spherical shell. Do you understand? So in electrostatics, it doesn't matter what the shape of the object is, how the charges are distributed, that's what matters more. Do you understand? So that means, so this can be a solid sphere but a conductor, or it can be simply a spherical shell. In any case, we need to find the electric field due to this spherical shell at a distance r from the center. Okay, let us find it. Now here, the point at which we find the electric field, so that can be inside or outside that sphere. Do you understand? So we have to consider two cases. Alright, in the first case, let us consider the point to be outside the sphere. Do you understand? So that is the first case. So outside. So we'll find the electric field outside that sphere. Okay, so that means what? The value of small r. So that is greater than the radius of the spherical shell given. Alright, so in this case, what is the electric field? Okay, let us use the same formula. What is the electric flux? So that equals, so E multiplied by A. So that is also equal to Q divided by epsilon 0. So this is the formula we've been using for all the questions of this type, right? Okay, now E multiplied by A. So we want the value of E. So simply divide by this area. So that will give you the answer. So what is this area? So that is the area of the Gaussian surface. So the Gaussian surface here is a spherical shell again. Alright. So that has radius small r. So that has area. What is the curved surface area of the sphere? So that is 4 pi r square. So that equals Q divided by epsilon 0. That's all. So simply we need the value of E. So divide this value. Okay, that's it. So E here is simply this value. If you divide, so 1 divided by 4 pi epsilon 0 multiplied by Q divided by R square. So that is the electric field due to the spherical shell. Okay. Now you can also write this formula in terms of K. 1 divided by 4 pi epsilon 0 can be written in terms of K. Alright. So either you write it in terms of epsilon 0 or K, doesn't matter. So the value of E here is, so if you write it as K, so that is KQ divided by R square. So that is the electric field due to the spherical shell. Okay. Yes. So this is the formula for electric field due to a spherical shell. Okay. So if you observe, this looks like the formula for the electric field due to a point charge. Okay. KQ divided by R square. So that is the electric field due to a point charge. So that means if you want to find the electric field due to a spherical shell at a point outside, so you can treat this spherical shell as a point charge. You understand? So this electric field due to a sphere or a spherical shell is same as the electric field due to a point charge. Okay, that is only when the point is outside. What if the point is inside? Okay, let us do this now. Suppose the point is inside, that means the value of r is less than the radius of the sphere given. Okay, inside. In that case, let us use the same formula. So what is the value of phi? So that equals, so E multiplied by A, so that must be equal to Q divided by epsilon 0. But what is the value of Q? But this time the point is inside. Now we draw the Gaussian surface again a sphere, but it is inside. So now you tell me, what is this Q? Q is the total charge inside that Gaussian surface. So what is the total charge inside that sphere? So that is 0 charge, because the charges are only on the surface of the outer sphere. So the inside Gaussian sphere has no charge. Do you understand? So the charge Q is 0 here. So that means this value is 0, because the charge Q is 0. The charge inside is 0. So that means E multiplied by A is 0. So that means the value of E is 0. That's all. So this is the electric field due to a spherical shell inside. Okay, at a point inside we have the electric field always 0. Okay, so remember that inside a spherical shell the electric field is 0, and outside we can treat it like a point charge. Okay, kq divided by r squared. Inside we have electric field 0. Okay, so that is the electric field due to a spherical shell. But let us draw the graph of the electric field versus the distance from the center. Okay, yes. Now if r is less than r, which means any value of r less than this capital R, the electric field is 0, which means, so from 0 to capital R, the value of this electric field is 0. Okay, flat like this. Okay, electric field is 0 if r value is less than r. Now when r is greater than r, okay, so when r is greater than r, so here it has value, it is a decreasing function. Do you understand? So denominator is r square. So as r tends to infinity, so when r becomes infinity, okay, so this value becomes 0. So as r tends to infinity, this value decreases to 0. Do you understand? So this is the graph of the electric field versus the distance. Okay, initially it is 0 up to that point r, then it increases, then it decreases till 0. Okay, at infinity the value of the electric field is 0. Do you understand? So that's all. So this is about electric field due to a spherical shell. Okay. So here we have a solid sphere. Okay, this time the charges are distributed over the entire volume. So obviously it is not a conductor then. So it is a solid sphere. Now we have to find the electric field due to this solid sphere. Okay, at a point at a distance r from the center. Okay. Now again we have to consider two cases. The point may be outside or inside the sphere. But when the point is outside the sphere, it is just same as the last one, right? So the spherical shell. So now we can treat this sphere as a point charge. Do you understand? Otherwise the same calculations can be done, but I am just writing it directly. So if the point is outside the sphere, you can treat this solid sphere as a point charge. So that means, so we have these two cases here. So again, outside. So that means the value of r is greater than the radius of the sphere. In that case, so we can consider this sphere as a point charge. So that's what we derived in the last case also. So instead of doing that derivation again, I'm just writing it directly. So it is like a point charge, or it is like a point charge. Okay, so for a point charge, what is the electric field? So that is the formula, the electric field. So that is simply kq divided by r square. That's all. So this is the electric field due to a solid sphere at a point outside the sphere. Okay, yes. Now that is done. Now we want the electric field at a point inside the sphere. Okay. That means the value of r is less than the radius of the sphere. Okay, in that case, but here it is different. Okay, it is not 0 if you consider a Gaussian surface. Okay, so that is again a sphere. Okay, so but the charge inside that Gaussian surface is not 0, because the charges are distributed over the entire volume. So there are some charges inside that Gaussian surface also. So let us use the same formula here. The electric flux equals E multiplied by A, so that equals Q divided by epsilon 0. E multiplied by A, so what is A? A is the area of the Gaussian surface, so that is area of the sphere, right? So that is 4 pi r square. So that equals Q. What is the charge inside that Gaussian surface? The entire charge is Q. Q is the, so the charge Q of the sphere okay, so that is the entire charge, okay, but that is not what we want. We want the charge inside, so this is only the charge inside, okay. So don't confuse this charge with the charge given in the question. You understand? So the charge here is charge inside that Gaussian surface, but this charge Q is the total charge of the sphere. So that is not to be substituted here. Alright, do you understand? Because this is only the charge inside the Gaussian surface. Okay, let us find that. See, the total charge of the sphere is what? That is Q. But we want only that smaller portion, okay, only the charge inside that. So that ratio should be same, right? The charges are distributed uniformly over the surface. So that means, so what is the volume of this sphere? So the charges are distributed just like the volume, right? So the ratio of the volume is same as the ratio of the charges. Do you understand? So what is the volume of the inside portion? So the volume of the inside portion is simply 4 by 3 pi r cube. Okay, this is the volume. So that divided by the total volume. What is the total volume? 4 by 3 pi r cube, capital R cube. So this ratio is same as the ratio of the charges. Do you understand? So that means this is same as the ratio of the charge inside divided by the total charge. Is that okay? So the ratio of the volumes is same as the ratio of the charges because they are uniformly distributed, the charges. So that's all. So this is the relation so we have to use. So from that we can write the charge inside. So that equals the charge Q multiplied by, so this is R cube divided by capital R cube. Okay, so that's all. So this is the charge inside that Gaussian surface. Okay, that can be substituted here. So this is Q R cube divided by this small r epsilon 0 R cube. Do you understand? So that's it. So simplify this, you should get the answer E. So that E here is simply, so if you divide by 4 pi, so it will become, so 1 divided by 4 pi epsilon 0 multiplied by, so 1 r gets cancelled, so this is Q multiplied by R divided by R cube. Okay, so that's all. So this is the electric field at a point inside that sphere. Okay, yes. Now you can write this 1 by 4 pi epsilon 0 as K, so that will become, so E equals, so this is KQ multiplied by R divided by R cube. So that's how, so this is the electric field due to the solid sphere at a point inside. Do you understand? So KQR divided by R cube. So that is the electric field due to a solid sphere at a point inside. But a spherical shell at a point inside, the electric field was 0, right? So here it is KQR divided by R cube. Do you understand? So that is the electric field due to a solid sphere. Now if you try to draw the graph of this function, it will be like this. See, when the point is inside, okay, when the point is inside, now this is a linear relation. You understand? These are all constant, KQ divided by R cube. That is the real, these are all constant. This R is a linear, okay, linear value. That means it will be like a straight line, okay, from 0 to R. 0 to R means inside. That means it is like a straight line. It increases, okay, linear relation. And here, when this R is greater than R, when this R is greater than R, so now it is R squared in the denominator, then it is a decreasing function. You understand? At infinity it will become 0. So that means it increases and then decreases. Okay, increases till the surface and then it decreases thereafter. Do you understand? So that is the graph of the electric field versus the distance from the center. Okay, so for the charge, okay, for a solid sphere. Do you understand? So that's it. So that is about electric field due to a solid sphere. Okay. Here we will find the electric field due to an infinite line of charge. See, we have already derived the formula using integration, right? So what is the formula for the electric field due to an infinitely long rod? So that is the formula.
2kq by r.
Yes, we will derive the formula again, but this time using Gauss's law. Alright, so there is an infinite line of charge at a point at a distance r from it. We have to find the electric field. So this electric field E, that's what we need to find. Now we have to find the Gaussian surface, the surface on which it has the same electric field at every point. See, apart from this point, is there any other point at which it has the same electric field due to this infinite line of charge? See, you draw this circle. At any point on the circle, it will have the same electric field because any point on the circle is at a constant distance from this rod. So the electric field will be same. Do you understand? So this circle has the same electric field. Okay, now, but we want Gaussian surface, not a curve. Circle is simply a curve, but we want Gaussian surface. So what is the surface on which it has the constant electric field? So that is the cylinder. Do you understand? So you take any point on the cylinder, so that point that electric field will be same at every point on the cylinder. Do you understand? So that means this cylinder is our Gaussian surface. But again there is a problem. So Gaussian surface should be a closed surface. Do you understand? Not an open surface like this. So we want a closed cylinder. What do you do? So you close this top and bottom. That's all. So this is the closed cylinder. Do you understand? So this is a closed surface. We find the electric flux, and from that you find the electric field. Do you understand? Just like how you did the previous questions. Do you understand? Yes. So this is a closed cylinder. Find the electric flux. So using electric flux you find the electric field. Alright. Yes. Now let us find the electric flux. But it is not one surface, it is a curved surface and also these two flat surfaces, right, the top and bottom. Alright, so we have three surfaces. You have to find the electric flux through all the three surfaces. Okay, electric flux through the curved surface plus the electric flux to the, say, top surface. Okay, I'll call it top. Okay, electric flux through the bottom surface. Okay, so that's it. So let us find the total electric flux. So what is the electric flux through the curved surface? So that is E multiplied by the area. Okay, the electric field multiplied by the area. But what is the area of the curved surface? So that is the curved surface area of a cylinder. So that is 2 pi r h. Okay, h is the height of the cylinder. So that is 2 pi r h. Alright, E multiplied by area. So that is the electric flux through this curved surface. Okay, done. Now what is electric flux through this top surface? See this top surface, this one, so that is parallel to the electric field. See this electric field due to this rod are in this direction, right? This direction, now horizontal direction. But the top surface, so that is already in horizontal direction. That means these electric field lines are parallel to these two surfaces. So that means what is the electric flux through this top surface? That is 0, because the surface is parallel to the electric field line. So as we have already seen, when the surface and the electric field lines are parallel, so in that case, so we have electric flux 0. Do you understand? So same goes with this, the bottom surface also, because that surface is also parallel to the electric field lines. Okay, so plus 0. So that means the electric field is only through this curved surface. Do you understand? So that is E 2 pi r h. That's it. Now, what is the formula for the electric flux using Gauss's law? So that is the charge divided by epsilon 0. The charge inside. Okay, the charge inside divided by epsilon 0. What is the charge inside that cylinder? We are not talking about the entire charge, right? The total charge of that rod. Okay, we only want the charge inside that cylinder. Do you understand? Only that portion. See, we are only given the charge density of that infinite line of charge. What is the charge density? Lambda. But what is the total charge? So that is the charge density multiplied by length. Do you understand? Because the total charge is the charge density multiplied by length. Because what is the formula for charge density? So that is the charge divided by length. Charge per unit length. So that means the total charge inside is simply the charge density, which is lambda, multiplied by that length. Okay, what is the length here? So length of the portion of the rod inside that cylinder. So that has value. So that is the height of the cylinder, right? The height of the cylinder is the portion of the rod inside the cylinder. So that has value h. So lambda multiplied by h divided by epsilon 0. So that's all. So that equals the same value. So here E 2 pi r h. So that's it. So if you do the simplification, we get the value of E. So E here equals, so if you simplify this, so we will get this h gets cancelled. So this is lambda divided by, so 2 pi epsilon 0 this r. So that's all. So this is the answer, the electric field due to the infinite line of charge. Okay, but if you want to write it in terms of k, so what is the value of k? So k value is 1 by 4 pi epsilon 0. Alright, so that means this value is 2k. Okay, so this is 2k. So 2k lambda divided by r. So that's all. So this is the electric field due to an infinite line of charge. Okay, 2k lambda divided by r. So that's all. So this is the formula you have to remember, the electric field due to an infinite line of charge. But we've already derived this formula and we have done many questions based on that also. But now we have derived the formula using Gauss's law. That's all. So electric field due to an infinite line of charge has the formula 2k lambda divided by r. Okay. Here we have an infinitely large plane of charge. We have to find the electric field due to this plane at a distance r from it. See, even this one we have already done. See, what is the formula if you remember? sigma divided by 2 epsilon 0. So that is the electric field due to this infinitely large plane. But now we will derive the formula again, but using this Gauss's law. Okay, so let us consider the point at a distance r from it. So we need to find the electric field at that point. Now as usual, we will find a surface on which the electric field is constant. Okay, see this surface, this Gaussian surface need not always be a surface having same electric field. You understand? At any point on the surface, the electric field need not be same. So the Gauss's law works for any surface, any closed surface, the Gauss's law works. But that is of no use for us. But we want a surface on which the electric field values are same. You understand? Otherwise, so we will not get the electric field at that point. So we want a surface on which the electric field values are same. You tell me, what is the surface on which we have the same electric field as this point? So you consider all the points which are at this constant distance r from that plane. Okay, so let us consider one disk, right? Circular disk. So any point on this circular disk will have the same electric field, because so this circular disk is parallel to this plane. So that means any point on that disk so will be at a constant distance from this plane. So that means they will have the same electric field. This can be considered the Gaussian surface. You can also consider another circular disk at the same distance but in the opposite direction. Okay, in this direction. So two circular disks. Okay, now we want a Gaussian surface. That means it should be a closed surface. So you close it. So we will consider a cylinder. You understand? You consider this cylinder. So that is treated as the Gaussian surface. Now you find the electric flux through the closed surface. Now from that we can find the electric field. Is that okay? So let us find it. So let us find the total flux. So the total flux here is the flux due to that the surface on the right. Okay, so that, what do you call, say right, plus the electric flux due to the surface on the left. Okay, this base of the cylinder. And also we have a surface, the curved surface of the cylinder. Okay, so now we'll find the electric flux through all these surfaces separately. So what is the electric flux through that base on the right? So that has radius, say r, right? Capital R is taken to be the radius of that circle. Okay, so then the electric flux has the formula, the electric field multiplied by that area. So area is pi r square. So pi r square. Plus similarly, what is the electric flux through this surface on the left? So that also has the same formula, right? Because this electric field multiplied by same area pi r square. Now what is electric flux through the curved surface? So this curved surface is like parallel to the electric field lines, because the electric field due to this plane is like this, right? Parallel, horizontal direction. Now this surface is also horizontal, right? This direction, so parallel. So electric field here is parallel to the curved surface. So that means the electric flux is 0. Do you understand? So that's all. So this is the total electric flux. Okay, so this gives you the value. But what is the formula for electric flux using Gauss's law? Okay, here we have used the basic formula of electric flux. So electric field multiplied by area. But now we will also use Gauss's law. So what is the formula for Gauss's law? Simply Q divided by epsilon 0. Do you understand? Simply Q. Q is the total charge inside that closed surface. Okay, but what is that total charge? So the total charge inside the surface. So only a part of the whole plane is inside that surface. Okay, so we have to find the total amount of charge inside that surface. Do you understand? So that has a formula. What is the formula for the total charge? So that is the charge density. Okay, surface charge density multiplied by area. So that is the formula for the total charge. Surface charge density sigma multiplied by the area of the part which is inside that closed surface. Okay, that is like a circular disc again. So that is the formula sigma, say pi r square. Okay, pi r square. So divided by epsilon 0. So that equals, so this is 2 times. So 2 e pi r square. Alright, so let us simplify this. So what is the value of, okay, so now some values get cancelled, right? So pi r square, so pi r square gets cancelled. So that will give you the value, so E value. So E equals, so this sigma divided by 2 epsilon 0. So that's all. So this is the formula for the electric field due to an infinitely large plane. Do you understand? Yes. Now if you observe, so this is independent of the distance r. Okay, which means at any point, at whatever distance, okay, you take any point, the electric field is constant. So this is one example of a uniform electric field, right? We've discussed this already. So this is independent of the distance r, because it is an infinitely large plane. So the small distance r does not matter. So even if, at a different point you find the electric field, so that will have the same value. Okay, sigma divided by 2 epsilon 0. So this is the electric field due to an infinitely large plane. Do you understand? So sigma divided by 2 epsilon 0. Okay? Yeah. Here also we have an infinitely large plane, but it is a conductor this time. So what difference does it make? See, we know that the charges are distributed on the surface of a conductor. See, even though it is a very thin sheet, still it has two surfaces. Okay, one on the left, one on the right. There are two surfaces. But if it is a non-conductor, like we did in the previous case, it can be treated like a one surface, okay, treated like one surface only. But if it is a conductor, even if it is a very small, very thin sheet, but still this is treated to be two surfaces, okay, one on the left, one on the right, because the charges are distributed on the surface of the conductor. So this is, the charges are distributed on these two surfaces this time, alright, not one surface. So remember this difference. If it is a non-conductor, so it is like a one surface, but for a conductor, so even though it is a very thin sheet, we will consider this to be made of two surfaces. Okay, so now we have two planes. Now instead of one plane, we have two planes. That means what is the total flux? So that is 2 times what we have derived previously. Do you understand? So that means simple it is, multiply the answer that we got in the last case by 2. Do you understand? So that's it. Simply here, this thin sheet of charges, so that is made of two surfaces. Okay, not one surface, two surfaces, because it is a conductor. So these two surfaces have electric field what? So what is the electric field due to one of the surfaces? So that is 2 times the electric field due to one surface that we have derived in the last case. So that is simply sigma divided by 2 epsilon 0. Do you understand? So this is the formula we have done previously, but now simply multiply this by 2. Okay, here. Now the electric field here is simply sigma divided by epsilon 0. So that's all. This is the electric field due to a conducting plane. You understand? Even though it is the same question as the last one, but this time we have a conductor. So this one sheet is considered as a combination of two surfaces. Okay, so it is like two sheets of charges. Do you understand? So the difference here is 2 times, so sigma divided by epsilon 0. Okay, yep. Electric field inside a conductor. We are already familiar with this idea, right? The electric field inside a conductor is 0. But anyway, we will use Gauss Law to derive this result. Okay. Now we know that in a conductor, the charges are distributed only on the surface. Okay. So inside the conductors, we don't have any excess charge. So all the charges of a charged conductor are distributed on the surface of the conductor only. So let us take a point inside the conductor. At that point, we'll find the electric field. Okay. Now you take a Gaussian surface. So any surface you take, see, take a sphere, okay, a spherical shell. This is a spherical shell. Now at that point on the surface we have this electric field. You have to find the electric field E. Okay, let us find it. Now what do we do? Same idea. So let us use the Gauss law to find the electric field. Okay, so this is the idea we've been using. So phi equals, as E is constant, we can use this idea, E multiplied by A. Okay, so the electric field at any point is taken to be constant, so phi is E multiplied by A by Gauss's law. So that is also equal to the charge inside divided by epsilon 0. Okay, so that's all. So we have the charge inside. What is the charge inside that spherical surface? So that is 0, because as we have seen, the charges are distributed only on the surface of the conductor. So inside the conductor we have no charge. That means inside our Gaussian surface we have no charge, which means the total charge inside the surface is 0. So that means here Q value is 0. That's all. So that means the value of E is also 0. You understand? So E is 0. So that's all. So this is the idea we have to know. Inside a conductor the electric field is 0. Okay. So electric field value is 0 inside the conductor. Okay. The electric flux through each face of a cube due to a charge Q placed at the center of the cube is. Here we have a cube inside which we have a charge Q placed exactly at the center of the cube. Now due to this charge Q we have some electric field, and due to this electric field we have some electric flux through all the 6 faces of the cube. This cube has 6 faces, which means 6 surfaces. You have to find the electric flux through all the 6 surfaces. Okay, yes. Now this charge q is exactly in the middle. That means this charge q is at equal distance from all the 6 faces. Do you understand? That means electric flux through all the 6 surfaces are equal. You understand? Because distances are equal, so all the 6 surfaces have the same electric flux. Do you understand? So that means you find the electric flux through one of the surfaces, so that will be same for the remaining 5 surfaces. Do you understand? Let us use Gauss's law to find the total electric flux. So what is the formula for the total electric flux? So electric flux total. So that equals, by Gauss law, the charge inside divided by epsilon 0. Alright, so the charge inside is q. So this is the electric flux through the entire cube. Okay, done. But that is 6 times the electric flux through each phase. Do you understand? Because each phase has electric field same. Okay, constant value. So that means this total is 6 times the electric flux through one of the phases. Okay, one phase. So that must be equal to q divided by epsilon 0. So we want the electric flux through just one phase. So that equals q divided by, simply divide by 6 epsilon 0. So that's also, that is the electric flux through each phase of the cube. Do you understand? Because by symmetry, so the electric flux is same for all the surfaces. So that means one of the surfaces has 1/6 of the total electric flux. Do you understand? So q divided by 6 epsilon 0. So that is the electric flux through each surface of the cube. Okay. The electric flux through any phase of a cube due to a charge q placed at one of the vertices can be. Here also we have a cube, but the charge q is not placed inside the cube. It is placed at one of the vertices. So we place the cube at one corner, we find the electric flux through all the 6 phases. Unlike the last question, here the electric flux is not same for all the 6 phases, because the charge q is not at same distance from all the phases. So that means the electric flux values may be different for different phases. Okay. So the charge q is placed at one corner. That means, say for example, you take one of the phases, okay, the top phase. Okay, so the top phase has this charge q at one corner. See, let us take this example. There is a square. Now at one corner, so we have the charge q. Now tell me, what is the electric flux due to the charge q through this surface?
0.
Why is it 0?
The electric field lines do not pass through the surface.
Yes, so the electric field lines due to this charge q do not pass through this surface. Do you understand? Because all the electric field lines are in the radially outward direction. So no electric field lines pass through this surface in the perpendicular direction. The perpendicular component of all the electric field lines through this surface, so that value will be 0. Do you understand? That means, so if you place the charge q at one corner of the square and find the electric flux, so that value will be 0. So that means we can conclude that the electric flux due to the charge q through that top surface, that is 0. Similarly, what is the electric flux through this surface, the left one? So that is also 0, because that also has one corner, so the charge q. Do you understand? Similarly, this surface, right, the front face, so that also has electric flux 0, which means these 3 surfaces, the electric flux through these 3 surfaces, so that value is 0. Do you understand? The other 3 phases, so that's what we have to find. Okay, but by symmetry we can also conclude that the electric flux is same for all the 3 other surfaces. Do you understand? Because this charge is at equal distance from all the other surfaces, which means you find the electric flux through one of the surface or one of the phases, so that will be same for the remaining 2 phases. Do you understand? So let us find the electric flux. But now we can't use the symmetry idea that we used in the last question. Alright, so there the charge was exactly in the middle, so we found the total electric flux and then we divide by the total number of phases. But we can't do that, but we have to bring in some kind of symmetry. Okay, what we do is some kind of construction we do, right? Now what you do, so this charge is at one corner of the cube, but now we want to get this charge in the middle. Okay, like the last question. Okay, how to get this charge in the middle? So what you do is, so you put different sized cubes, okay, adjacent to this, so like this. Now, so there are 7 more cubes. Okay, totally we have 8 cubes. Now you consider this big cube. So this big cube has charge q exactly in the middle. Do you understand? So now we have constructed a bigger cube which has this charge q exactly at the center. Do you understand? Now we can use the same idea that we used in the last question. Okay, now what is the total charge or the total flux? So the total flux here equals the charge inside charge q divided by epsilon 0. So this is the total electric flux through the entire cube, okay, that bigger cube. Do you understand? Okay, but that bigger cube has how many faces? Okay, so how many faces are there in the bigger cube? So that each face, 6 faces are there, so that is this square, the bigger square. But we want the electric flux through that smaller square. So there are 6 faces. This bigger cube has 6 faces, but each face has 4 smaller faces. Do you understand? So that means 6 multiplied by 4, so that is electric flux through each face. Do you understand? So this bigger cube has 6 faces, okay, 6 bigger squares, but this each bigger square has 4 smaller squares. So we want electric flux through the smaller squares only. So which means 6 multiplied by 4, so the electric flux through each smaller face. So that equals this total value. So that is Q by epsilon 0. So that's all. So this will give you a required answer. So the electric flux through each phase, that equals, so this value, so 24. So Q divided by 24 epsilon 0. So that's all. So this is the answer. So this is the electric flux due to the charge Q through these 3 phases. Okay. See the other 3 phases of the cube. So the electric flux through them, so that is 0, because all the phases inside this cube have electric flux 0. Okay, passing through them. So only the outside, okay, exterior phases, so they have the electric flux this value, Q divided by 24 epsilon 0. Do you understand? So coming back to the smaller cube, so the electric flux through these 3 phases, so that is this value, Q divided by 24 epsilon 0. Now what is the electric flux through the other 3 phases? That we have already found, so that is 0. Do you understand? So that's all. So this is the answer, electric flux through all the, each phase of the cube. Okay, done. An infinitely long line of charge density lambda is along y-axis. The electric flux through the square of side A parallel to yz plane at a distance root 3a by 2 from the origin is. We've already done a similar question in electric flux. If you remember, there is an infinite line of charge along y-axis, okay, and also there is a square plate which is parallel to yz plane. We have to find the electric flux due to this infinite line of charge through that plane. Okay, so we have done already this question in electric flux, but at that time we only used the basic formula of the electric flux, right? So E multiplied by the area. Now we will use the Gauss Law to find the answer. Okay, so let us find it. Now let us use Gauss Law. So that means you have to find the total flux, the Gaussian surface. You have to find the Gaussian surface. But first of all, the electric flux due to this line of charge, okay, and also the area is known. So is it simply electric field multiplied by the area? No, because this area is not perpendicular to the electric field lines. Okay, so this area is not perpendicular. Okay, so what do you have to do? You take the projection. Okay, you take the projection of the area. Do you remember the idea that we used there? If you take the projection, that plane will be bent and it will become a curved surface. So that will be part of a cylinder. If you complete that curved portion, it will be a cylinder. But here only a part of the cylinder. So that part of the cylinder area is what we need. Do you understand? So that area multiplied by the electric field will give you the answer. Or we can use Gauss's law also. Okay, let us find the total flux. So the total flux due to the whole cylinder. See, we don't have the whole cylinder. We only have a part of the cylinder, only a small curved portion of the cylinder. But first of all, we will find the electric flux due to the whole cylinder. Okay, yes. So that has the formula by Gauss's law. So that is Q or Q in divided by epsilon 0. So the total charge inside that cylinder. See, we want a Gaussian surface, right? What is the Gaussian surface here? That cylinder only. So that cylinder is the Gaussian surface. Okay, you can close this, right? Top and bottom can be closed here. So it is a closed cylinder. So that is our Gaussian surface. What is the total charge inside that Gaussian surface, which means that cylinder? See, the charge here is only due to that line of charge, okay, but only a portion, okay, a small part of that line is inside the cylinder. Now what is the amount of charge contained in that part of the line? So that is simply the linear charge density multiplied by the length. So what is total charge? The linear charge density multiplied by the length. So this value is simply the linear charge density lambda, okay, multiplied by the length of the portion which is inside that cylinder. Okay, so that is simply taken as L, so divided by epsilon 0. That's it. So that is the electric flux through the whole cylinder, but that's not what we want. We only want the electric flux through only a small portion of the cylinder. Okay, yes, that small portion makes angle. What is the angle subtended by this portion at the center? So that is 2 theta, right? Here half of the value is taken as theta, so that means 2 theta is the total angle. But what if it was a complete cylinder? If it is a whole cylinder, that will subtend angle 360 degree, right? 2 pi is the total angle, but this is only a fraction. The total cylinder subtends angle 360 degrees, which means 2 pi. But this is not the total angle, it is only 2 theta, right? Only a fraction of that, 2 theta, which means that fraction of this value will be our required flux. This is the flux due to the whole cylinder. Now, we want to find flux only through that part, which means the fraction. So what fraction here? So that is in the ratio of the angle, right? So what is the angle subtended by this part? That is 2 theta. What is the angle subtended by the entire cylinder? So that is 360 degree. So that's all. So that fraction. So that means our flux through our required curved part, okay, the curved part, which means so that portion of the cylinder whose electric flux we need to find, okay, the electric flux through that curved part is what we need. So that portion is simply the ratio of the angle, okay. So that is, what is the angle subtended by this part? That is 2 theta. Angle subtended by our required part divided by the total angle. The total angle is 2 pi, right? 360 degrees. So that ratio, okay, multiplied by this total. So lambda L divided by epsilon 0. Do you understand? So that is our answer. But what is the value of this theta? Okay, that you have to find. Okay, so what is the value of tan theta here? So that is simple geometry, right? Tan theta. So use some basic trigonometry. So tan theta here is equal to, okay, so that is a right angle triangle, right? So right angle triangle, and the length of the side, okay, of the base, so that is half of the side of the square. So that is a by 2 divided by, so that adjacent side, so that is root 3a by 2. So that means this will give you the value of theta, or tan theta equals, so this gets cancelled, so 1 divided by root 3. So that means theta here is pi by 6, okay, so 30 degrees. So that's all. So this is our required angle theta, so that can be substituted here. Do you understand? Substitute here theta, so that is pi by 6. The 2 gets cancelled, so pi divided by 6 divided by pi lambda L divided by epsilon 0. So what do you get the answer? So simply we get lambda L divided by 6 epsilon 0. That's all. So this is our required answer. So that is the electric flux only through that part of the cylinder. Do you understand? So that means that is the answer, the electric flux through the given plane. So that is the square plate. Do you understand? So we found the electric flux through the entire cylinder using Gauss's law. Now only the part we need, so that ratio we use here, okay, only that small part of the cylinder. So this is only a fraction of the total. The total is this one, the fraction of the total is the required answer. Do you understand? So lambda L divided by 6 epsilon 0, okay. See, this L and A are same only here because it is a square, so the length and breadth both are same. So L or A doesn't matter. So lambda A divided by 6 epsilon 0, okay. The electric flux due to the charge Q inside the closed surface given in the figure is. We have a closed surface here inside which we have a charge Q. Now we need to find the electric flux. The electric flux through this closed surface, that has the direct formula Q divided by epsilon 0 by Gauss's law, but we only need the electric flux through the curved surface, right? The other surface is a flat surface which is a circular disc. So we can find easily the electric flux through a circular disc, but we want the electric flux through that curved surface. The electric flux through the entire surface, so that has the formula Q by 2 epsilon 0. So that is simple, but we only need the electric flux through the curved surface. So this is a weird shape, right? So we don't know the area, nothing about that, but still we have to find the electric flux through that surface, okay? So let us find it using Gauss's law, okay? First of all, let us find the electric flux. What is the total electric flux? So that by Gauss's law, it is Q divided by epsilon 0. So that is the total electric flux. What is meant by total electric flux? It is the electric flux through that curved surface and also the electric flux through that circular disc. Okay, so that is electric flux through the curved surface plus electric flux through the disc. So this total is only Q divided by epsilon 0. But what we need here is the electric flux through this curved surface only. Do you understand? For that we need to know the electric flux through the disc. Okay, how will you find it? See, we've already done this if you remember. So we've already found the electric flux through a circular disc in the last class. Okay, while we were discussing electric flux, at that time we found the value of electric flux through a circular disc. If you've forgotten that thing, so you can refer to this video, right? So in the last class we have discussed this. Now I'm not going to derive that result, so that we are going to use directly. Okay, so that formula. So here the formula is, so the electric flux through the curved surface plus electric flux through the disc at a distance x on the axis. So that as a formula. So Q divided by 2 epsilon 0 1 minus x divided by square root of x squared plus r squared. So that must be equal to the same value, Q divided by epsilon 0. Okay, so this is the electric flux through a circular disc. Okay, that we have already done. So we are making use of that result. Okay, yes, that's all. Simply you have to find the electric flux through the curved surface. Just do these calculations, you will get the answer. That's all. So the electric flux through the curved surface equals, so this minus this. Okay, so this is Q divided by epsilon 0 minus Q by 2 epsilon 0. So that is Q by 2 epsilon 0. So Q divided by 2 epsilon 0. And then this minus that goes to the other side, that will become, so this value can be taken out, right? Q divided by 2 epsilon 0 multiplied by x divided by this. That means simply you will get 1 plus x divided by square root of x squared plus r squared. So that's all. So that is the electric flux through the curved surface. Do you understand? So this closed surface is a combination of two surfaces, but one is a known shape. Okay, that is a circular disc. The other one is an unknown shape, but still the total flux is also known to us, and the electric flux through that known surface, that is a circular disc, so that is also known. So using that you find the electric flux through that unknown shape. Okay, so that's all. Simple. Do you understand? So that is the answer to the question. Okay. Yes. Two concentric spherical shells of radius small r and capital R have the surface charge density sigma. The electric field at a distance x from the center can be. Here we have two concentric spherical shells having charge density sigma. We have to find the electric field at a point at a distance x from the center. Okay. Now here we don't know whether the point is outside or inside or between these two spheres. So we have to consider different cases. Do you understand? Let us consider the first case where the point is outside both the spheres, which means the value of x is greater than the outer radius, which is r. Do you understand? That means the point is outside both the spheres. Okay, yes. Now let us use Gauss's law. Okay, how will you do this? Let us find a Gaussian surface. What is the Gaussian surface here? Another concentric shell. Do you understand? Another sphere. Okay, so that is our Gaussian sphere, because there we have the electric field value same. At any point on this sphere, the electric field has the same value. So that means, so that is our Gaussian sphere. Now let us find the electric flux. So what is the electric flux formula? So that is E. E is constant, so E multiplied by A, that's it. So that equals the charge inside divided by epsilon 0. So that is the formula. Now let us find the area. So what is the area of that Gaussian sphere? So that has radius x. So x is the radius, so the curved surface of the sphere. So that is, so E multiplied by that area is 4 pi r squared, which means 4 pi x squared. So that equals the charge inside. See, this time both the spheres are inside that Gaussian surface only, which means the total charge of these two spheres, so that is our charge inside our closed sphere. Do you understand? Yes. Now let us find it. What is the charge inside the sphere? Say one of the spheres. Okay, let's take the bigger sphere. So what is the charge? So that is the charge density multiplied by the area. Okay, what is the total charge? The surface charge density multiplied by the surface area. So this is the surface charge density multiplied by the surface area of the bigger sphere. That is pi to 4 pi r square. Similarly, what is the total charge inside that smaller sphere? So that also has the same formula, the charge density multiplied by the area of the surface. So the charge density is same in both the cases. So that is same sigma multiplied by that area is 4 pi. The radius of that is r square. Do you understand? The charge density multiplied by the surface area, that is the total charge. So this value divided by, okay, so this epsilon 0. So that's all. This will give you our required electric field. Okay, so the required answer here is, so what gets cancelled? See, this 4 pi gets cancelled. So we'll get sigma r squared plus r squared divided by, so x squared. Okay, epsilon 0 x square. So that's all. So this is the answer. The electric field at a point outside both the spheres. Do you understand? That is just one of the cases. So the electric field when x is greater than the bigger radius, so that will have electric field at a point at a distance x. So this formula. Okay. Now the next case where so x is less than r but greater than small r, which means so this time the point lies between these two spheres. Okay. So x lies between small r and capital R. So which means now we will take our Gaussian surface, which is again a spherical shell but which contains the smaller sphere only, the outer sphere, right? That is outside the sphere, right? The bigger sphere is outside our Gaussian surface. That means so the same formula here. So what is the formula? So same phi equals E multiplied by A. So that equals the charge inside, okay, divided by epsilon 0. So that's all same formula, but this time, but what is the charge inside? So this is same thing, E multiplied by 4 pi x squared. But what is the charge inside? The inside charge is only due to the smaller sphere, okay, not both the spheres, only that smaller sphere, only this value. Do you understand? So that means it is simply sigma 4 pi small r squared, okay, only this sphere is inside. So divided by this epsilon 0. Okay, done. Now we'll get the value of E here. So this value of E is, so cancel this 4 pi, so we'll get sigma r squared divided by so x squared, so epsilon 0 x squared. Okay, done. So that's it. So that is the electric field due to, okay, but here this time the value of x is between this small r and capital R, so between these two spheres. Okay, done. Now there is also another case where x is less than r. This time x is less than r, less than small r. So that means our required point is inside both the spheres. Okay, then what is the formula? So this time the electric flux is E multiplied by A, so that equals the charge inside. What is the charge inside? So this time the Gaussian surface is inside both the spheres, all the charges are outside this Gaussian surface, which means inside the Gaussian surface we have no charge. So the total charge is 0, right? So that means this value becomes 0 because the charge inside is 0 in this case. So what is the electric field in this case? So that means, so E here is 0. So that is the answer. So these are the three possible answers. Do you understand? Depending upon the value of x. So we have three different possibilities. So electric field can be either this or this or this. Do you understand? So all these are answers. A solid sphere has charge density varying with the distance r from the center as rho equals m multiplied by 1 minus r by r. The electric field at a distance x greater than r from the center of the sphere is. Here we have a solid sphere. That means the charges are distributed over the entire volume. Okay, so we have to find the electric field due to this charged sphere at a distance x from the center. But the value of x is given to be greater than r, which means we just have to consider a point outside the sphere only. Okay, so no problem with that, just one case. But the charges are not distributed uniformly. At different points the charge density, right, the volume charge density rho, so that has this formula m multiplied by 1 minus r by r. So that is not a constant, it depends on the distance from the center. Small r is the distance from the center. So that means at different points the charge density is different. Do you understand? So that means we can't find the total, we have to find the total charge here actually, because so how to find the electric field at a point? We have to use Gauss's law. So we take a Gaussian surface, okay, that having radius x, so that is the Gaussian surface which is a spherical shell. Now we have to find the total charge inside, because the formula is simply the charge inside divided by epsilon 0, that is the electric flux. So the charge inside, what is charge inside? That is the total charge of the sphere. But to find the total charge of the sphere, but it is a variable charge distribution. Do you understand? So simply, generally, if the charge density is given, multiply that by volume. The volume charge density rho multiplied by the volume will give you the total charge. But here the problem is it is not a constant, it is variable. At different points we have different charge density, so you have to use integration. Okay, so let us consider a small point at a distance, say r, okay, from the center. Okay, we consider a sphere. So that has some thickness, okay, it is a hollow sphere but it has some thickness dr which is very small. So because this thickness is very small dr, so over the entire sphere we consider the charge distribution to be constant. Because this thickness is very small, all the points on the sphere are at the same distance small r from the center, so that means the volume density, so that is considered to be constant on this sphere. Okay, yes, now after doing integration we can get the total charge of the entire sphere. Okay, so let us find it. So first of all, the charge due to that small sphere, okay, that shell, okay, charge, so that is dq, okay, only due to that small thing, okay, not the entire sphere. So dq, so that is given by, what is charge formula? So that is the charge density, okay, volume, charge density, rho multiplied by the volume, charge density multiplied by volume. But volume is not the total volume, volume of only that small portion, okay, that sphere, okay. So that volume will give you, multiplied by the charge density is the total charge, okay. Yes, now we have to do integration to get the charge of the sphere, so that we can do later. Let's first simplify this. So this is rho multiplied by dv. What is dv? dv is the volume of that sphere, okay, only that small portion, okay, not the entire sphere, only that small thickness, okay. So that volume we have to find. What we have to do is, we will find the volume of the outer portion having radius r plus dr, subtract the volume of the inner sphere, so that is having radius r. Do you understand? So what is the volume of sphere? It is 4 by 3 pi r cubed. But what is r there for the outer sphere? That is small r plus dr. So that is 4 by 3 pi r plus dr cube. That is the volume of the outer sphere. Now what is the volume of the inner sphere? So that has radius r, so that means 4 by 3 pi r cube, okay. So that means we can write it as, if you take this out, it will become r cube, okay. That's it. And this rho is given in the question, okay. So that is given to be m multiplied by 1 minus r by r, okay. So that multiplied by this one, 4 by 3 pi. Yes, let us simplify this. So a plus b cubed, right? So that is a cube, r cube. So that r cube get cancelled. Next 3a squared r. So that is 3a squared. This r squared dr. And the next term is 3a r squared. Which means dr squared. But we usually omit all these terms, right? Dr squared, the higher powers of dr, because dr is very small. So the higher powers only take dr. So dr squared, cube, all these values are ignored. So that means simply this much. Do you understand? So that's all. So this is the value of dq. Now we want to find q. So how to find q? Simply integration. So if you do the integration, we'll get the value of q. So that equals, so let us do the multiplication. So these are all constants. So 3 gets cancelled, 4 pi m. Yes, 4 pi m multiplied by, so multiply this, 1 multiplied by r squared. That is r squared, and r by r multiplied by r squared. So that is r cube divided by r, okay, dr. So we have to do the integration, okay. So where r, the small r ranges from 0 to capital R, okay. So we have to take the value of r 0 initially, and then the maximum value is the capital R. So that is 0 to r, okay. Just do the integration, we should be able to get the answer, that's all. So this is simply 4 pi m r squared. Integration is r cube divided by 3. After substituting this upper limit, which is capital R cube divided by 3, this is r to the power 4, so that will get cancelled. So I'm writing directly, this is r cube divided by 3. So after substitution, you'll get this one. Minus, this is r to the power 4 divided by 4. 1 r will get cancelled. So that is again r to the power 4 divided by, sorry, r to the power 3 only, because that r gets cancelled. 1 r gets cancelled. So divided by 4. Okay, simplify this, we will get 4 minus 3, 1. So r cube divided by 12. So which means pi m r cube divided by, so this is 12, and then 4 gets cancelled, divided by 3. Okay, so this is the charge. What is charge? The total charge of the sphere, okay, the entire sphere, the total charge is this one, pi m r cube divided by 3. Now we have to use Gauss law. Okay, how to use Gauss law? Simply let's find the electric flux. So the same formula. So let us find the electric flux. So that equals E multiplied by A. So that equals, so the charge inside divided by epsilon 0. Okay, so E is what we need to find. So E multiplied by the area of the Gaussian surface. The area of the Gaussian surface is, so that is the sphere, right? So the curved surface area of the sphere. So that is 4 pi r cube. So that is r squared. So that is x squared. Okay, that equals the charge inside. What is charge inside that Gaussian sphere? So that is same as the charge of the solid sphere. That is what we are finding. Just to find the value of q, we have done all this calculation. You understand? The charge of the sphere. So that is this one, pi m r cube divided by 3. So that you have to substitute there. That's all. Okay. So this is pi m r cube divided by 3 epsilon 0. That's all. This will give you our required value of this electric field. So electric field here is simply multiply, 1 pi gets cancelled, so this is m r cube divided by, so this is 12 epsilon 0 x square. Okay, so that's all. So this is the required electric field, alright, due to the solid sphere at a distance x from the center. Do you understand? So that's all. So that is the answer. Okay.
If the point is inside the sphere,
If the point is inside, that means the value of x is less than the radius of the sphere, then we can use the same idea, almost the same idea, but this time the Gaussian surface will be inside the sphere. Okay, that means we only need the point inside that Gaussian surface, which means a sphere of radius x, not the sphere of radius r. You understand? That means instead of integrating from 0 to r, we can only integrate from 0 to x. Do you understand? That is the only difference, because the Gaussian surface is inside, the total charge is only from 0 to x. Alright, so the charge inside the sphere of radius x, not r. So 0 to x. So integrate from 0 to x. So accordingly the answer will change. Okay. So but the same idea of integration, but only the limit changes. Do you understand? So whether the point is inside or outside, so we can follow the same steps. Okay. So that is the total electric field due to the given solid sphere. Okay. An infinitely long rod has linear charge density lambda. A charge minus q of mass m revolves around it at a distance r. Its speed depends on. There is an infinite line of charge having charge density lambda, and also there is a point charge minus q at a distance r. This point charge revolves around this line. This revolution happens because of a centripetal force. So the revolution happens only because of the centripetal force towards the center. But this centripetal force is due to the attractive force between these two charges, right? So that force is provided by the electric field. Do you understand? There is an electric field due to this line of charge, and due to this electric field there is an electrostatic force, and that electrostatic force is the centripetal force here. Alright, so simple centripetal force formula we have to use. So the centripetal force, so what is the formula for the centripetal force? So that is mv squared divided by r. So that is centripetal force, and that centripetal force here is due to this electrostatic force. Okay, so that is Fe, I'm writing Fe, the electrostatic force towards the center. So that is the centripetal force here. Okay, yes. So but what is electrostatic force? Mv squared by r here equals, the electrostatic force is the charge multiplied by the electric field. Okay, so force is same as the charge multiplied by the electric field. So the charge q multiplied by the electric field. I'm only taking the magnitude, okay, minus q, but we just need the magnitude, the positive value. Okay, right. But what is the electric field at that point? Due to this infinite line of charge. So that has a formula, right? So this is, okay, mv squared by r. So that equals, so q multiplied by the electric field due to the line of charge at that point. So that has the formula 2k lambda divided by r. So this is the formula for the electric field due to an infinite line of charge. So 2k lambda divided by r. That's it. Simplify this, you will get the required value of v. That's all. So we'll get v squared equals, so simplify this. So r gets cancelled. So we can divide by m. So this is 2k lambda q divided by, so this m. That's it. So we can find the value of v taking a square root of this. So v equals square root of this value. So 2k lambda q divided by m. That's all. So this is the value of v. Okay, but this v contains m, which means v depends on m. M is the mass of that charge. Okay, yes. Similarly, v also depends on lambda, q, everything. So but there is no r, which means this v is independent of r, the distance, which means wherever the point is, okay, the distance doesn't matter, the velocity or the speed remains the same. Okay, the speed is same, so that is independent of the distance from that line. So r, do you understand? So that's all. So this value is independent of the distance r. Do you understand? So that means it depends on the rest of the factors like lambda, q and m. Okay. A hemispherical shell has uniform charge q. The electric field at a point P given in the figure makes angle theta with the base of the hemisphere. Then theta is. here a hemisphere is kept like this, okay, and there is a point on the base, right, on the flat surface there is a point. At that point you have to find the electric field or the direction of the electric field. That point is at some distance from the center. It is not exactly at the center, at some distance from the center. So we have a point. At that point we have to find the direction of the electric field. But here it looks like an acute angle, okay, it is given to be an acute angle, but we don't know exactly whether the angle is acute or obtuse like this or it is a right angle perpendicular. We don't know exactly. That's what we need to find. But just for reference, it is given to be an acute angle. It is drawn like that here, but we are not sure. So let us find the angle theta, whether it is acute or obtuse. So that you have to find. Okay.
Most of the charge is on the left side. The electric field must be away from it. It must be an acute angle.
Yeah, most of the charges are on the left side of this point. That means the electric field will be pointing away from these charges, which means intuitively you get an idea that this angle will be an acute angle. But I am not sure. Let's see whether your logic works. Suppose we assume that this is an acute angle, okay, as given in this figure. Now we have two components, one in the horizontal direction, E cos theta, one in the vertical direction, so E sin theta. So this electric field has two components, horizontal and vertical direction. Okay, now what we are going to do is we will consider another hemisphere of same shape. Okay, so let us take another hemisphere of same shape. You keep it upside down, okay, like this. Now at the same point on that hemisphere also we have electric field, but again the angle is acute, okay. That means it will have two components, one in the horizontal direction E cos theta, one in the vertically downward direction E sin theta. Do you understand? So these two hemispheres have different vertical and horizontal components. Okay, now what you do, you join these two spheres. Suppose you join these two hemispheres, you get a complete sphere, okay, one sphere. If it is a whole sphere, that means what is the electric field at that point? So we know that electric field at a point inside a spherical shell, so that is 0. That means for the whole sphere, which means the combination of these two hemispheres, the point has electric field. At that point the electric field is 0, okay. But we don't have the whole sphere, we only have a hemisphere. So let us find one by one. First, what is the electric field due to the whole sphere? So that we will find. So the electric field due to the whole sphere, okay, I'm writing like this, the whole sphere. So that is 0, okay. So the whole sphere, inside we have electric field 0, okay, done. Now what is electric field due to the whole sphere? That is the total electric field due to the sphere, the lower half and the upper half. So separately, so this is the electric field due to, so this is a vector form, okay, the electric field due to the lower sphere plus the electric field due to the upper sphere. So that total must be equal to 0, okay, yes. But what is the electric field due to that lower sphere? So that has two components, okay. So that is E, okay, E is the magnitude of the electric field, but it has two components, one cos theta I cap. So this horizontal direction I cap, so cos theta I cap. So that is one component in the horizontal direction, cos theta I cap. Similarly, there is a vertical component E sin theta j cap, okay. So we'll write like this, sin theta j cap. That's all. This is the electric field vector at the point due to that lower sphere. Similarly, so let us find the electric field due to this upper sphere. So that is E multiplied by, again it is a horizontal component, same direction I cap. So that means E cos theta I cap. And also it has a vertically downward component, right? Vertically downward. So that is component in the direction minus j cap. That means this is minus sin theta j cap. You understand? That total must be equal to 0 because we have the total electric field inside the sphere 0. Okay, so that's all. Let us simplify this. So this gets cancelled, right? Sin theta j cap minus sin theta j cap, that gets cancelled. So E cos theta I cap plus the same value, that means 2 times. So that must be equal to 0. So you tell me what is the value of cos theta then? 0, right? So these are all constants. So cos theta is 0. Cos theta is 0. That means what is theta? So theta equals say 90 degrees. So theta equals 90 degrees. Do you understand? That means theta is not an acute angle. So that is exactly 90 degrees. Do you understand? That is a right angle. So that means the electric field at that point is actually pointing in the vertically upward direction. Do you understand? So theta is 90 degree. So not as given in this figure. So the actual angle is 90 degree. So this electric field is in the vertically upward direction. Okay?
Why didn't my logic work?
See, your logic could have worked if all the charges are of same distance from that point. See, on the left we have more amount of charge, but the distance is also more. On the right, we have less amount of charge, but they are closer to that point. You understand? So the distance compensates the amount of charge. Do you understand? See, something like this. So we have more charge. We have less charge here, but the point is closer here. So this compensates, the distance compensates the amount of charge. Do you understand? So that is why, so we have the angle 90 degree exactly. Do you understand? So logically we didn't arrive at this conclusion, but after doing this calculation, so we got the answer, so 90 degree. So that is our answer. So the direction of the electric field is in the vertically upward direction. Is that okay? Yeah. A solid sphere of radius r having charge density ρ has a spherical cavity. The distance between their centers is a. The electric field inside the cavity is. A solid sphere is given, but it has some cavity. So this cavity is also in the form of a sphere only. So that means a smaller sphere is removed from this sphere. Now we have to find the electric field due to this remaining portion at a point inside this cavity. Alright, so there is a point inside this cavity. We have to find the electric field due to only this remaining part of the sphere. Okay, yes. Now what do we do? Simple. We will assume that this sphere has no cavity, which means it is a full sphere. Now we will find the electric field due to this whole sphere. Then subtract the electric field due to that cavity. That means the removed portion. Because that portion is removed, we will subtract the electric field due to that portion. Alright, yes. What do you do? Let us assume a point. Okay, there is a point inside this cavity at a distance say r1 from the center of this bigger sphere and r2 from the center of the smaller sphere. Okay, that cavity. Okay, now let us find the electric field due to the bigger sphere. First of all, we will assume that this sphere has no cavity. Now we will find the electric field. Okay, so how to find the electric field? At this point, so but the electric field is only due to the inner circle, right? The inner sphere, okay, not the outer portion, because so we know that the electric field due to a spherical shell is 0. That means the outer portion does not contribute to the electric field at that point. Okay, only the inner sphere. So let us find the electric field only due to the inner sphere, then subtract the electric field due to that cavity. Alright, yes, let us find one by one. So the electric field due to the whole sphere. So that is denoted by say E1. So our required E vector, so that equals the electric field due to that the sphere, the whole sphere, okay, that minus the electric field due to the cavity, so that is E2 vector. Okay, so E1 vector is this one along this R1 vector and E2 is along this R2 vector. So that difference will give you the answer. Okay, let us find E1. What is the electric field due to this inner sphere? So that has formula. Okay, so what is the electric field due to a sphere? So that is K Q divided by the distance. The distance is R1 square. Okay, KQ divided by R1 square multiplied by R1 cap. Do you understand? So that is only the magnitude and multiply this by that vector along that direction of the electric field. So that is R1 cap. Okay, done. Now minus the electric field due to the cavity. So that is KQ divided by R2 square multiplied by R2 cap. So this is the required electric field. Okay, yes, let us simplify this. What is this Q? Q is the charge inside the sphere of radius say R1. Okay, so only due to that smaller portion of the sphere. So now let us find the total charge inside the sphere of radius R1. Okay, but what is the formula for the charge? So charge equals the charge density multiplied by the volume. You understand? The charge density multiplied by volume. What is charge density? That is rho. Okay, so that means K multiplied by rho. Rho is the charge density, volume charge density multiplied by the volume. So what is volume? So that is 4 by 3 pi radius cube, which means R1 cube divided by, so this is R1 squared multiplied by R1 cap minus, similarly here. Okay, so here also we have K rho. Now the volume. So volume here is 4 by 3 pi, R radius is R2. So R2 cube divided by, so R2 squared R2 cap. Okay, done. Let us simplify this. So we can take out common factors like 4 by 3 pi K rho. R1 squared gets cancelled, right? Which means simply R1. So R1 multiplied by R1 cap minus R2 multiplied by R2 cap. You understand? So that's all. Now what is R1 cap? See, R1 is the magnitude of the vector. R1 cap is the direction of the vector. So magnitude and direction, that means that vector only, right? This is the magnitude of the vector and direction of the vector. That means it is simply R1 vector. So this is R1 vector. This is similarly R2 vector. So this is 4 by 3 pi K rho R1 vector minus R2 vector. Okay, so that's it. Now let's simplify this. What is this k? K can be written as 1 by 4 pi epsilon 0. So let's write the answer in terms of epsilon 0. So 1 by 4 pi epsilon 0. So this 4 pi also gets cancelled. So we'll get the value in terms of this rho divided by 3 epsilon 0 multiplied by r1 vector minus r2 vector. What is that value? See, consider this triangle. In this triangle, one side is r1 vector, the other side is r2 vector. So the third side is r1 minus r2, right? That is the triangle of vector addition, right? So r1 vector is one side, r2 vector is the other side. So r1 minus r2 is the third side. So third side is, say, this length, so OP vector. Okay, it's the vector, say OP vector. Suppose O is the center of the bigger sphere and P is the center of the smaller sphere. So that vector joining the OP vector. So that is the required electric field. That's all. So this is the answer. But we want the magnitude of the electric field. So that is, so rho by 3 epsilon 0. So the magnitude of OP. So what is the magnitude of OP? So that is the distance between the centers of the two spheres. Okay. So what is the distance? So that distance is given to be A, right? The distance between the centers. So that is A. So that means the magnitude of this OP vector. So that is A only. So that's all. So that is our required answer. You understand? So this is the electric field due to that sphere with the cavity. Do you understand? So what did we do here? So we found the electric field due to the entire sphere, okay, without any cavity. Then subtract the electric field due to that portion which is removed. Okay, that's all. We also remove, right? Subtract the electric field. So that will give you our required answer. Okay, so rho A divided by 3 epsilon 0. Okay. Consider a uniform spherical charge distribution of radius r1 centered at the origin O. In this distribution, a spherical cavity of radius r2 centered at P with the distance OP equal to A equal to r1 minus r2 is made. If the electric field inside the cavity at position r vector is E of r, then the correct statements are. So it is the same question that we have done just now, right? So there is a solid sphere, it has some spherical cavity, we have to find the electric field at some point inside this cavity, alright? So if you remember that result, so what is the electric field due to this sphere? So that is rho divided by 6 epsilon 0 multiplied by this OP vector, okay, the vector form. So this is the result that we derived in the previous case. Now you tell me, so what is this OP vector? So that is the vector which joins the two centers, okay, the centers of these two spheres. So that means what is the magnitude of this electric field? So that has value rho divided by 6 epsilon 0 magnitude of OP. So that is the distance between these two centers, okay. The distance between these two centers is taken as, say, A, okay. That's all, rho A divided by 6 epsilon 0. So this is the electric field. Now does this depend on the position of the point? See, A, that is the distance between the centers, okay, that is always constant. Rho is a constant anyway, so all these values are constant, which means the electric field is a constant value, so it is uniform electric field. So what does it mean? At any point inside the cavity, the electric field is same, constant. You understand? So uniform electric field. Not only the magnitude, even the direction, right? What is the direction? OP vector. So OP vector is in the horizontal direction. So the direction is also same. You understand? So that is given to be A vector, right? So A vector is along this, the vector joining these two centers. So this depends on A. Okay, so the magnitude depends on the value A, and also the direction is A vector, so that also depends on A. So that means the electric field is uniform, okay, over the entire volume. So that means at any point inside the cavity, so we have the same value for the electric field, okay, so this value, and the direction is also in the horizontal direction, okay. So the A vector, the vector which joins the two centers, so that vector is the direction of the electric field, okay. So that's all. So the answer must be an infinitely long thin non-conducting wire is parallel to the z-axis and carries a uniform linear charge density lambda. It pierces a thin non-conducting spherical shell of radius r in such a way that the arc PQ subtends an angle 120 degree at the center O of the spherical shell. The permittivity of free space is epsilon 0. Then which of the following statements are true? Here we have a spherical shell and also an infinite line of charge which pierces the sphere, which means a portion of this line is inside the sphere. Now we have to find the electric flux through this surface of the sphere due to this infinite line of charge. Alright, simple application of Gauss Law. Alright, simply use Gauss Law, we will get the answer. Alright, so what is Gauss Law? So the electric flux, Okay, so that equals the charge inside divided by epsilon 0. That's all. So that is direct application of Gauss law. What is the charge inside? That's what we need to find. What is the charge inside? So this charge inside the sphere is only due to the portion of this line inside the sphere. So it is like this. Okay, so it is like this. This is a line. Do you understand? So this is the line, only that portion. It's an infinite line, but we don't want that. We want only that portion which is inside that sphere. Okay, but what is the charge? What is the formula for charge? So that equals the linear charge density lambda multiplied by the length. Okay, so length divided by epsilon 0. Alright, so what is the length of that portion of the line inside the sphere? That's what we need to find. Okay, simple. So this is the line inside the sphere. So now it subtends angle 120 degrees. So that means what is this angle? Half of the angle, that is 60 degrees. The total angle is 120 degrees. So this is 60 degrees. So this is the radius of the sphere. That means what is this length? So that length is the vertical projection, right? R sine 60. R sine 60 equals this value divided by R. So this value is R sine 60 degree. Or that can be written as R root 3 divided by 2. So that is only half of our required length. Okay, so this is the portion inside that sphere, but the half of the length is R root 3 by 2. That means what is the total length? So twice of that. So that is simply lambda multiplied by that length is R root 3 divided by, so this epsilon 0. That's all. So that is our required answer. That's it. So this is the total electric flux due to the infinite rod through this surface. Okay, so lambda R root 3 divided by epsilon 0. Okay, done. And we also need to find the direction of the electric field. Now we have the electric field due to this infinite rod. What is the direction of the electric field due to an infinite rod? That is in the perpendicular direction, right? At any point in space, the electric field will be in the perpendicular direction. So this is the direction of the electric field. So that means at any point on the sphere or anywhere in space, the z component, that means the vertical component of the electric field is 0. You understand? Because this is an infinite rod, the electric field is in the perpendicular direction. So this is the direction. So the electric field in the vertical direction. So that is 0. So z component of the electric field is 0. So that is one answer. So Ez, so z component is 0. Do you understand? So the answer here is, so this is the value of the electric flux, which is lambda R root 3 divided by epsilon 0, and also the electric field in the vertically upward direction. That means that component of the electric field is 0. Okay. So here ends our discussion on Gauss's law. In the next class, we'll be doing electric dipole. Bye for now.